Alright, so we're on to 4.2 here. We're going to go ahead and start out with number 1. Basically, we're just trying to find all the critical points on these graphs here and see which ones are maximums or minimums. Okay, so I think we have a global maximum at 3.5-ish, right in between 3 and 4. And I think that's just about all we have on the graph here. Okay. Alright, skipping to number 5. Basically, they give us the function and we need to find the global maximum or minimum for the closed interval. So basically, they're giving us a function and then they're cutting it off. They're saying it's only from here to here, so in our problem we have that the x's are only allowed to go from -3 to 1. Okay, so I would encourage you to graph a lot of these. You can just kind of plug in these equations, but we're doing basically the same thing that we've been doing for local minimum and maximum. Here we find the derivative, which I have here, and then this step I'm just setting it equal to 0 and I'm skipping a step. I'm moving the 16x over to the other side. That's the step that I'm skipping. So basically we have to divide by x and divide by 4, and we get that x squared equals 4, so x equals plus or minus 2. But x can't equal positive 2 because positive 2 isn't in this interval here. Okay? So you can only test the critical points that are in the interval. So you want to test the endpoints. We want to test 1 and -3. And you also want to test -2. So you plug all 3 of those into f of x, the function, not the derivative. You plug them back into the function. Okay. So that's what I'm doing here. I'm plugging the endpoints of our interval. Our interval goes from -3 to 1. So I plug in -3, 1, and then -2 because -2 is a critical point. And I'm just trying to find out which of these 3 have the highest values and the lowest values, because that'll tell us if they're global maximums or global minimums. And just for kind of an example here, it's kind of similar to if we had like some sort of graph and then our interval was like from right now how it's from -3. Well, I'm going to cut off my answer there, but that's -7. But say our interval goes from -3 to 1 just like it does there, and our graph is doing something here. It could be doing a lot of different things, right? It could have maximums at the endpoints here. So that's why we need to check the endpoints to see if, basically to see if they're going to be global maxes or not. Or it could have global minimums down there. It could have a graph like that. Or we could have a graph that doesn't have either. It kind of goes like that and goes like that. It doesn't have either at the endpoints, and that's why we'd have global max and mins there. So we just need to test those endpoints. That's very important. Test the critical points and the endpoints. Alright, so number 7 here. Just doing the exact same thing. We're going to go ahead and basically we're going to take the derivative. Once we take the derivative, we'll set it equal to 0. So I've taken the derivative. Once you multiply by 1/3, that 3 goes away out in front, and you have to subtract by 1, so you get -2/3. Okay. And so basically what I say here is, x to the -2/3 means that you have to move it to the bottom. Okay. and then I multiply both sides by that. That way we can get an x to the positive 2/3. And so now we have x to the positive 2/3 equals 1. And I was thinking about how to solve this. I think you would take some sort of square root that's like a 2/3 or a 3/2 or something like that. But when you think about it, everything, 1 times 1 in any fashion is going to be itself. So the answer there is just x equals 1. So we want to plug in 1, -1, and 8 into the f of x up here, this equation, to see what values are the highest and the lowest for local maxes and global maximums and global minimums. Okay, so we plug all those in and see which one's the largest and which one's the smallest. The largest will be the global max and the smallest will be the global minimum. Okay, perfect.